marks worth of question, where in which, as you can see over the screen in here, so number of 1 mark questions were in total of 5, and the number of 2 marks question were asked in total of 8. So summing up, you get around 21 marks. So on an average in GATE exams, you'll have marks. I mean, the range of marks that they keep in is like 20 to 25. 25 is the max for most cases. So this is the norm that they follow while setting up GATE papers. Okay, so let's get started. So this is the first question. So a conventional altimeter is dash. So we have 4 options in here. One is pressure transducer, temperature transducer, density transducer, and velocity transducer. So altimeter. So as the name suggests, so it's basically altimeter means you measure the height, right? So let's say this is my mean sea level, and let's say this is at some altitude, h. Okay, let's take that. Basically, when you measure the altitude, what happens is, you know, if you go back to my hydrostatic equation, dp equal to minus rho g dh. Let's take h as the uh, axis. Let this be x as the axis. So in here we have dp equal to minus rho g dh. So which means when you measure a change in altitude, we can basically infer the change in pressure, right? So basically this is the key idea in here. So if I know the change in altitude, I can know the change in pressure. And change in pressure is detected by what? A sensor, so which is basically a pressure transducer. Okay. So this is my answer for the first case. That's for the first one. Okay. Let's go to the next question. Take this down. So the relation between an airplane's true airspeed VTAS true airspeed and equivalent airspeed VEAS in terms of the density ratio, which is sigma equal to rho by rho naught, where rho naught is the air density at sea level and rho is the air density at the altitude at which the airplane is flying, is given by the formula. So we have 4 formulas in here: V equivalent airspeed, V true airspeed, and we have 4 formulas in here. So let's try how to do this. Okay. Basically, how do you approach this problem? Let's see that. So we have 4 airspeeds in here. One is my indicated airspeed. Another is my CAS, which is my calibrated airspeed. Another is my equivalent airspeed. And this is my true airspeed. Okay. So generally, when an aircraft is flying at mean sea level, the speed that an aircraft measures is the V equivalent airspeed. Okay. And at some altitude, no, at some altitude, right? The speed that it measures is basically the true airspeed. So in a sense that your dynamic pressures at both altitudes must be the same, because your density drops and velocity increases. That is, you can fly at a much higher velocity. So which means the dynamic pressure will be same. Let's say at altitude, some altitude, half rho V TAS square. This has to be equal to half rho V EAS square. So which means if I simplify this, so this should be rho naught. Okay. So mind you, rho naught is at mean sea level, rho is at some height h. Okay. So from here, if we simplify this, let's bring this. What are the options given? If you go back in here, so it's VEAS by VTAS. So let's bring VTAS to the side, which means VEAS by VTAS whole square is equal to, I have rho by rho naught. So which means what? VEAS by VTAS is equal to under root of rho by rho naught which is equal to root of sigma. Sigma is the density ratio. Okay, so which is my option C. Okay, I hope you don't have any doubts in this. If you have any doubts, please leave your questions in the chat box. Okay, right. So let's go on to the next question. An unswept fixed wing aircraft has a large roll stability if the wing is placed low on the fuselage and has a negative dihedral angle, low on the fuselage and has a positive dihedral angle, high on the fuselage and has a negative dihedral angle, high on the fuselage and has a positive dihedral angle. So we have to think about this. So let's see how to do this. If you look at the question, unswept fixed wing aircraft, okay. Has a large roll stability. Let's underline these keywords first. Unswept fixed wing aircraft, large roll stability. Okay. Now, if the wing is placed, let's say like this, so what happens is basically, your roll stability is destabilized. This is from the theory. If you place it like this, okay. So that's why to counteract this, we give in a dihedral so that the roll stability is improved in here. And this is by giving a dihedral. On the other hand, if you have an aircraft which has a high wing, so in this case, it is the most stable aircraft. Let's say if you give it a further dihedral like this, it will become more and more stable. So which means that you are making the aircraft to be more stable, and thereby you lose a control of the aircraft. So that is an undesirable case. So what you do is you basically, try to give unhedral to the aircraft in here. By giving unhedral, we reduce the stability so as to attain controllability. Okay. So which means if I go back to my equation, let's read the sentences. Low on the fuselage, there is a negative dihedral angle. Okay, so let's look at the sense as well. So this sense is a positive dihedral. Okay, so this is a positive, and this is a negative dihedral. Okay, so mind you, please be careful with that. Okay, let's go back to the options again. So low on the fuselage, and as a negative, so which means let's draw adjacent over here. Low on the fuselage and as a negative dihedral, which is like this. Low on the fuselage and as a positive dihedral like this. High on the fuselage and has a negative dihedral angle, which is like this. High on the fuselage and has a positive dihedral angle, which is like this. So which means my option is now B. But mind you, you should also have a controllability in here. Okay, so that's why so you first achieve a controllability effect. We say that if the wing is placed low on the fuselage and if it has a positive dihedral angle, then we say that an aircraft has large roll stability. I hope you guys don't have any doubts on this. Yeah, true. But see, lunatic eagle, I understand. But thing is, see, if let's assume, roll stability, meaning, I mean, let's come back to the diagram in here, Okay. So roll stability means you should understand that the rolling, I mean, it should be able to stabilize, right? Let's say some gust wind is coming and no aircraft tilts to one, rolls to one side. So the roll stability should be such that it should restore back to its original state. When you have this high wing with a large roll like this, what happens is instead of coming back, it basically overshoots. The reason is because of the strong lateral stability in here. That is, let's say, let me try to draw this in here. Let us consider this one. Let's say aircraft is initially here. After some disturbance, uh, let me draw a black colored one so that you understand that the aircraft position is now here. Now, when this will obviously restore, right? But what happens is instead of stopping at this red one, it will overshoot this red, and basically reach this point. That is, this will be a new aircraft position, which means it has stability, but it's trying to overshoot because of the very strong stability. Okay, so in this sense, my option B should be the correct one. Okay, hope you understand. Let's go on to the next one. So the thrust available from a turbojet engine increases. So we have four options in here. Increases as altitude increases up to the tropopause and then decreases. Remains constant at all altitudes. Decreases as altitude increases. So again, we have to think about how to approach this. This is pretty simple. So recall that my force thrust equation F is equal to m dot times V minus VA plus P minus PA times AE, right? So this is my thrust coming from the momentum, and this is the thrust coming from the pressure. You can write this pressure thrust, and you can write this as momentum thrust. So which means now if you see from this relation, F is proportional to, I can say this as m dot, right? So which means what? I can say F is proportional to, because m dot is rho AB, right? So which is, what can I say? F is proportional to rho, right? So which means what will happen if altitude increases, right? So if altitude increases, I write it in here. So if altitude increases, my density drops, right? So which means what? Force drops, correct? So which is the correct option? So D is the correct one. Hope you guys understood this one. Okay. So then let's go on to the next question. If CMCG, if the pitching moment coefficient about the center of gravity of an aircraft, and alpha is the angle of attack, then dCmCg by d alpha is dash. There are four options in here. A stability derivative which represents stiffness in pitch, a stability derivative which represents damping in pitch, a control derivative in pitch, positive for an aircraft that is stable in pitch. So this is not so straightforward, but maybe I can give it to you in writing as well, because this naming convention, this is unique for each and every paper. Some authors, prefer some, let's say, if you take some Russian papers, they will write some different notations. If you use some American papers, they'll use some different notations. Okay, so I just give it to you. So in general, if I have a DCM by DCL, just give me a second. Let me write it over this slide. So my DCM by DCL is basically a damping in pitch, whereas a DCM by D alpha is a stiffness in pitch. Which means if you go back to this thing, so stability which represents stiffness in pitch has to be the correct one. Copy this case. Right, so let's go on to the next question. Airplane flying at 100 meter per second is pitching at the rate of 0.2 degrees per second. Due to this pitching, the horizontal tail surface, located 4 meters behind the center of mass of the airplane, will experience a change in angle of attack, which is, so we have four options, excuse me, 0.01 degree, 0.008 degree, 0.04 degree, and 0.004 degree. Right? Okay, let's try to do this again. Let's infer from the data what is given. Airplane flying at 100 meter per second. Okay. So my V infinity is 100 meter per second. He's saying it's pitching at the rate of 0.2 degrees. So my Q is 0.2, 0.2 degrees per second. Next. And the LT is given as 4 meter. Right. So which means what? What will be my angular velocity? Just try to draw it as this is my CG. Which means my angular velocity omega would be simply q times LT, right? So that would be what? So it is basically 0.2 degrees. So to multiply it to convert it into radians into your 4. And if you simplify this, you will get it around 0.01396 meters per second. So in GATE exam, you can write down until the fourth number. Okay, you should have at least four numbers in a decimal so that you don't have any confusion, right? So which means what will be my I know from equation that it's not angular velocity, it's tangential velocity. Mind you. From I know from thin airfoil theory that so let's say I have a free stream wind coming in like this. Let's say V infinity. Let's say this is the downwash coming in. So which means this is my angle of attack. This is the downwash angle. So which in this case is my angle of attack. So I can write simply as tan alpha as W by V infinity. So from here I can write alpha as tan inverse of W by V infinity, which is basically what? Tan inverse of 0.01396 divided by V infinity is 100. So if you simplify this, tan inverse, okay. So you get close to 0.008 degrees. Okay. I should put this symbol in here because it's close. I'm approximating. So the correct option is obviously my option B. Hope you guys understood. Okay. Right. Let's go ahead to the next question. The contribution of the horizontal tail to the pitching moment coefficient above the center of gravity of an aircraft is given by Cm tail is 0.2 minus 0.0215 alpha, where alpha is the angle of attack of the aircraft. The contribution of the tail to the aircraft longitudinal stability is, so I have four options, is stabilizing, is destabilizing, is nil, cannot be determined from the given information. So let's do that. So write it down. So my Cm is given as 0.2 minus 0.0215 alpha. Generally, you can write Cm as Cm naught plus Cm alpha times alpha. Okay. So which means if I compare this with this, I can simply say that Cm alpha is basically minus 0.0215. This is one way. Other way is to differentiate this Cm with respect to alpha and you get the same value. Now, if my Cm alpha, which is dou Cm by dou alpha, if it is less than 0, then my aircraft is stable. Okay, that's the inference. Okay, whereas if dou Cm by dou alpha, if it is greater than 0, which implies my aircraft is unstable. So which means from the given information, what can we say is basically, my aircraft is stable. Okay. because my Cm alpha is negative, less than 0. Hope you guys understand. Okay. So if no doubts, let me go ahead. And I might have some audio delay. I don't know about it, but I will respond to your questions. So if I'm not able to note your questions in the chat box, fret not. I'll be there available. Okay, till 10:30. Right. So let's get to the next question. The linearized dynamics of an aircraft in straight and level flight is governed by the equation dx by dt is equal to abcd times x bar, where x is uwq theta vpr phi transpose. This matrix transpose represents the transpose of a matrix. A, B, C, and D are 4 cross 4 matrices, and 0 is the 4 cross 4 null matrix. Which one of the following is true? We have four options in here. A not equal to 0, B not equal to 0, C 0, D not equal to 0. A equal to 0, B not equal to 0, C not equal to 0, and D equal to 0. A not equal to 0, B equal to 0, C equal to 0, and D not equal to 0. And A not equal to 0, B equal to 0, C not equal to 0, D equal to 0. Okay. So let's write that matrix down. So I have this thing, right? So let's write that. dx by dt is basically A, B, C, D times. So in general sense, my A is basically this is basically representing the dynamics of the system. That is, in dynamics you have two parts, right? So we have the longitudinal dynamics, and the other we have a lateral directional dynamics. So these two are coupled basically. Change on lateral has an effect on directional stability as well. You can look at spiral roll and spiral divergence and Dutch roll and all. Okay, refer RC Nelson. It will be helpful for you to understand, right? So in general, my matrix A is basically the it contains elements, right? So if you recall the long period matrix, the long matrix, so you'll have a big matrix, right? So basically a 4 cross 4 matrix, wherein you should have all those elements. I'll just explain what that matrix is. So the matrix A is basically consisting of elements or the parameters which explain the effect of longitudinal disturbance on the longitudinal motion. So matrix A explains this. Okay. Next, matrix B explains the effect of lateral directional disturbance on the longitudinal motion. Next, matrix C explains the effect of longitudinal disturbance on the lateral directional motion, and the matrix D describes the effect of lateral directional disturbance on the lateral directional motion. Right? So which means I can say so longitudinal disturbance affects your longitudinal motion. That is so which means that your A cannot be zero, right? Next. Will any disturbance in the lateral directional plane affect your longitudinal motion? Of course not, right? So which means your B has to be zero. And same goes for C. Any change in longitudinal disturbance does not affect the lateral directional because your longitudinal is decoupled from the lateral directional. And your lateral directional disturbance, of course, affects the lateral directional motion. Hence, your d cannot be equal to zero. So, which means if you go back, and which is the option that is close enough to this, option C, right? So, you can mark that. Hope you have understood this, right? No doubts, then let me go ahead. The next question. The velocity vector of an aircraft along its body fixed axis is given by v vector equal to uvw. If v is the magnitude of velocity, alpha is the angle of attack, and beta is the angle of side slip, which of the following set of relations is correct? So we have four relations: u equal to v sine beta cos alpha, v equal to v sine beta, w equal to v cos beta sine alpha. U equal to v cos beta cos alpha, v equal to v cos beta, w equal to v cos beta sine alpha. Then we have u equal to v cos beta cos alpha, v equal to v sine beta, w equal to v sine beta sine alpha. U equal to v cos beta cos alpha, v equal to v sine beta, w equal to v cos beta sine alpha. Okay. So let's derive that first. To do that, let's try to draw an aircraft first. Let's understand the angles. Let's say this is the aircraft in a plane, basically. Okay, let's consider an axis system like this. Let's say that we fix the body. We are fixing consider an aircraft to be stationary, and we are allowing the wind to move over it. Okay, that's what we are doing in here. So let's say that use a different color so that you can visualize that. Let's say the wind is approaching at an angle alpha, where alpha is this angle. Excuse me for that. So alpha is my angle of attack in this case. And let's say that your beta is this angle, where if I try to represent it this way, beta is my angle in this plane. Okay, hope you guys understood. So this is my relative wind coming in. Uh, this is my v vector, and so if I try to project it onto this plane, so you'll have one use a red color. So on this plane, this dotted plane, so this projection will simply be this would simply be v cos beta, correct? And this velocity would be what? V sine beta, correct? That is, if I try to now draw this, let me draw this once over here. So you have a velocity vector coming in, and on this plane you're projecting this v cos beta. This is v, and this is my v sine beta. So this is my beta angle. Now this is my horizontal vertical, and with respect to the vertical, this is my alpha. So which means this component will be what? This component is basically v cos beta, and we're taking a component of this, so this will be cos alpha, and on this you will have v cos beta sine alpha. Okay, so going by our convention, u is the velocity in this axis, and v is the velocity in this axis, and w is the velocity in this axis. Which means if I write it down over here, so this will be what? So u is equal to my v cos beta cos alpha, then v is my V sine beta, which is simply this part alone. Okay. Then W is my this component. V cos beta sine alpha. This is the vector that we are looking for. So which means if I try to go back to the option and select the most appropriate one, it would be option D. Cos beta sine alpha. Yeah. So D is my correct option. Again, okay, so hope you guys don't have any doubts. So let me repeat what I just said in here. So you have this velocity, right? So you have V coming in. Let's say it is at an angle of alpha with respect to the vertical plane, at an angle of V beta with respect to the plane in the VW plane. Okay. So now you're projecting this. Okay. If I this is the drawing. So I'm projecting this. So this will be V cos beta and V sin beta. Now I'm projecting this V cos beta along the horizontal axis, which is this one, which will be my velocity, V cos beta cos alpha. And again, projecting this V cos beta with respect to the angle vertical. So this will give me V cos beta sine alpha. Okay. So that's what we have the velocities in here. Hope you guys don't have any doubts in this. Okay. Then let's go to the next question. An aircraft of mass 2500 kg in straight and level flight at constant speed of 100 meter per second has available excess power of 10 power 6 watt. The steady rate of climb that it can attain at that speed is dash. So underline the word the steady rate of climb. So what is my rate of climb formula? Is V sine gamma. Okay. So which gamma is basically the climb angle. Okay. This can also be written as excess power divided by the weight of the aircraft. Which means if I just substitute there's a formula value, so which means this will be excess power is 10 power 6 divided by weight of the aircraft is 2500 into 10. Let's take G as 10, so that, I mean, it doesn't matter, but because all the values are in hundreds, hundreds and they don't have decimal value, so let's take G as 10 for simplification. So this will give answer as 40 meter per second. Just 9. If an exam they're asking it as an NAT type, so please take G as 9.8. Okay, so that's the exact value 9.807, and you simplify that and you put it in the your NAT box. Okay, that's what you should be doing. Right. So let's go to the next question. If you have any doubts, a symmetrical airfoil section produces a lift coefficient of 0.53 at an angle of attack of 5 degrees, measured from its chord line. An untwisted wing of elliptical platform, an aspect ratio 6, is made of this airfoil. At an angle of attack of 5 degrees relative to its caudal plane, this wing would produce a lift coefficient of dash. Again, let's try this. This is again a tricky question, but nonetheless, it's pretty simple. So let's underline the keywords in here. Symmetrical airfoil section. It produces a lift coefficient 0.53, angle of attack 5 degree. Untwisted wing is made of this airfoil. Underline the word aspect ratio. At an angle of attack 5 degree, this wing would produce. Okay. Which means let's determine the lift curve slope. Because that's what we need. Okay. So how do you determine that? Let's say denote it. It's basically my dou CL by dou alpha, right? Which is my CL minus CL naught by alpha minus alpha at 0. Which means this should be, he says that it is at 0.53 divided by, it should be 0.53 minus 0 by, it's at 5 degree. So let's take it as 5 minus 0. So if we divide it, so A would come around 0.106 per degree. Okay. So this is the lift curve slope of the airfoil. Okay. Now for the wing, my lift curve slope will change. Okay. So let's use A3D. Okay. So that will be simply A by 1 plus A by pi EAR. Okay. So if we substitute it over here, so we'll have 0.106 1 plus 0.106 divided by pi EAR. So what is if you substitute the values again further? We go back to the previous one and elliptical platform. For an elliptical platform, your E is 1 because it has highest efficiency and aspect ratio 6. So which means 0.106 divided by 1 plus 0.106 because it is in per degree. You have to convert everything into per radians. Okay, so this is everything is so multiply this by 180 by pi, multiply 180 by pi, simplify this. Okay, so you will get pi times 1 times aspect ratios. What is that? 6. So this will give rise to a value of 0.08 per degree again. Okay, so which means if I substitute it back, so my CL would simply be 0.08 times 5, which is zero point 0.4. So this is my answer, and you can mark it 0.4. Copy this, guys. Hope you guys don't have any doubts in this. So please be careful in this step, particularly, while converting from per degree to per radian. My advice would be to convert everything into per radian so that you don't have any hassle in doing calculations. Okay. So at this step itself in GATE exam, you just convert this value directly to per radians and then go ahead. Okay, there's nothing wrong in it. Okay. But when you keep it to per degree, then there is the hassle. Okay, so please be careful. So I'll just write it in here so that you can later rewatch it. Right. So if no doubts, let me go to the next question. So we have a common data question. The roots of the characteristic equation for the longitudinal dynamics of a certain aircraft are lambda 1 equal to minus 0.02 plus 0.2 I. Lambda 2 is minus 0.02 minus 0.2 I. Lambda 3 is minus 2.5 plus 2.6 I. Lambda 4 is minus 2.5 minus 2.6 I. Where I equal to root of minus 1. So this is the first question. The pair of eigenvalues that represent the Fugard mode is dash. So I have four options in here: lambda 1 and lambda 3, lambda 2 and lambda 4, lambda 3 and lambda 4, lambda 1 and lambda 2. So again, this is a pretty simple one. Okay. So let's get started. So a longitudinal quartic, it's of this form. Okay. So you have a lambda power 4 plus b lambda cube plus c lambda square plus d lambda plus e equal to 0. If you solve this, you will get two quadratics. And if you solve these two quadratics, you will get two set of complex roots. This is, mind you, for a longitudinal case. Okay. For lateral directional, it will vary. We'll look at that sometime. Okay. So let's say the roots are now lambda 1 comma 2 is eta plus or minus I omega. Okay. And lambda, let's say eta 1 I omega 1. Lambda 3 comma 4 is eta 2 plus or minus I omega 2. Okay. Now, if I go back, no, I have omega 1 and omega 2. Let me rewrite those roots in here. So lambda 1 comma 2 is simply what? Minus 0.02 plus or minus 0.2. Okay. Then lambda 3 comma 4 is simply minus 2.5 plus or minus 2.6 I. If I watch it in here, you see my omega is high in the third 3 4 root, omega is low in here. So if you recall the Fugard motion, your omega is very small in Fugard, okay, whereas your omega is large in short period because it is highly damped, right? So which means the frequency will be higher, right? So which means my answer is my lambda one and lambda two will correspond to the Fugard mode, okay. So mind you, in Fugard mode, it takes a lot of time, so which means the angular frequency has to come down. Short period is basically happening in a short period, so which means angle frequency has to be higher. So this is my short period. So they asked for Fugard, so our answer is my option D, which is lambda one, lambda two. Okay. Hope you guys don't have any doubts in this. If you guys have any doubts, please do ask me. Okay, I'm here to help you. Put it in the chat box. I'll respond it later on or instantaneously, depending upon when I see it. Okay, we are here to help you. Okay, so let's look at question number next question because it has two questions. Again, the same data, the short period damped frequency. Okay, underline the word short period damped frequency. So go back to the previous problem that we solved. So we have the short period, right? Which is what we infer, right? So because my omega is small, so this is my Fugger, and omega is large, so this is my short period, right? So basically, if you look at the short period, so this is my omega part, which is my damped frequency part. Hence, your omega would simply be 2.6. So which is my option A. We are basically comparing it, okay? So mind you, please be wary of this, okay? You have to, problems like this are very easy to solve, but they appear monstrous in nature. So the best way to approach is you are given the roots and you're basically asked to determine the short period or the long period damped frequency. Okay. So, like I said, use this trick and it will be helpful for you while approaching the questions in the GATE exam. Okay. Right. So, if no doubts, let me go to the next question. Okay, guys. So with this, we wrap up the GATE questions, which was asked in the year 2009. And thank you once again to the people who are assembled in here. And please subscribe to IGC channel. And if you have any doubts, please put in the chat box. And let me repeat once again what I just said. No, please, refer to R.C. Nelson and Perkins and Hayes, some standard books, so that is helpful for you, while solving questions which are similar to the ones asked in GATE exam. Okay, right, guys. So the floor is open to questions. So you can post any questions in the chat box.